Everyone knows Switzerland conquered the Alps with precision engineering. Rack railways, electrification, mountain-conquering designs that became the gold standard for extreme terrain. But in 1937, deep in the archives of the Turkish State Railways, engineers were studying something that would challenge that narrative entirely. Test results showing a Turkish-built steam locomotive outperforming Swiss Alpine technology on grades the Europeans said were impossible. The locomotive was the Karakurt, built at the Sivas railway workshops in central Anatolia, designed specifically for Turkey's own brutal mountain crossings. And when Swiss engineers reviewed the documented performance data, they couldn't explain it. How had a steam engine from a railway system they dismissed as backward-achieved tractive effort figures that surpassed their own specialized Alpine designs? The story begins not in the Alps, but in the Taurus Mountains of southern Turkey. By the 1930s, the Turkish State Railways faced a crisis. The main line connecting the Mediterranean coast to the Anatolian plateau climbed gradients that would make European engineers wince. Sustained grades of 2.5%, curves tight enough to derail anything with a long wheelbase, and elevation changes of over 1,200 meters in less than 80 kilometers. The imported European locomotives, German, British, even Swiss designs, were struggling. They overheated on long climbs. They slipped on wet rails. They consumed coal at rates that made the routes economically unviable. Turkish engineers at Sivas proposed something radical, design their own locomotive from scratch, purpose-built for these conditions. The proposal was met with skepticism. Turkey's railway workshops were seen as repair facilities, not design centers. But chief engineer Fahri Engin had studied the problem obsessively. He'd measured wheel slip on every imported type. He'd calculated heat dissipation rates in mountain air. He'd analyzed why Swiss rack locomotives worked on Alpine grades but required infrastructure Turkey couldn't afford to build. His solution bypassed the Swiss approach entirely. Instead of rack systems or articulated frames, Engin designed a conventional steam locomotive with an unconventional distribution of weight and adhesion. The Karakurt used a 2-10-2 wheel arrangement, but with a twist. The middle 6 driving wheels carried 65% of the locomotive's adhesive weight. It concentrated over the point of maximum tractive effort. The boiler was mounted at a slight forward angle, keeping water over the firebox crown even on steep grades. And the cylinders used a compound expansion system that extracted every possible joule from each kilogram of coal. The first Karakurt rolled out of Sivas in 1936. It weighed 128 tons in working order. Driving wheel diameter, 1,350 millimeters. Boiler pressure, 16 kilograms per square centimeter. Tractive effort at 85% boiler pressure, 24,800 kilograms. On paper, these were respectable numbers, but the real test would come on the rails. The proving ground was the Pozanti-Ulukisla section, a 42-kilometer stretch that climbed 820 meters through the heart of the Taurus Range. Grades averaged 2.5%, with sections hitting 2.8%, curves as tight as 300 meters radius. And in winter, in temperatures that could drop to -20 Celsius at the summit, while the Mediterranean coast 80 kilometers away sat at 15 degrees. The first test run carried 480 tons up the grade. The Karakurt maintained an average speed of 18 kilometers per hour on the steepest sections without wheel slip. Coal consumption, 52 kilograms per kilometer. The German locomotives that normally worked the route consumed 68 kilograms per kilometer for the same tonnage and averaged 14 kilometers per hour, with frequent stops to build steam pressure. Engineers documented everything. Boiler efficiency remained above 72% even on sustained climbs. The compound cylinders extracted enough energy from exhaust steam to preheat feed water, reducing fuel consumption by an additional 8%. And the weight distribution meant wheel slip only occurred at loads exceeding 550 tons on wet rail, 150 tons more than any other locomotive type on the roster. Turkish State Railways built 6 more Karakurts between 1937 and 1939. But here's where the story takes a turn into the archives. In 1938, Switzerland was hosting an international railway engineering conference in Bern. The topic, mountain railway technology. Turkish State Railways submitted a technical paper detailing the Karakurt's performance data, including direct comparisons with Swiss AE 3/6 electric locomotives on equivalent grades. The paper showed the Karakurt achieving higher tonnage per kilometer figures on similar gradients, using readily available coal rather than hydroelectric infrastructure. For Switzerland, which had invested billions in electrification and rack systems, this was an uncomfortable revelation. A steam locomotive from Turkey, built in workshops that lacked the precision tooling of Swiss manufacturers, was matching their specialized mountain technology. The Swiss response was telling. The paper was acknowledged but not published in the conference proceedings. Instead, it was filed in the technical archives with a note questioning the measurement methodology. Swiss engineers argued that Turkey's gradient calculations might differ from European standards, that the test conditions weren't comparable, that sustained performance over decades, not months, was what mattered. But the numbers were verified. A Swiss inspection team visited Turkey in 1939, shortly before the outbreak of World War II. They rode in the cab of Karakurt No. 3 up the Pazanti grade. They measured the gradient with Swiss instruments. They timed the ascent. They calculated fuel consumption using their own methods. And their report is buried in the archives of the Swiss Federal Railways, confirmed everything the Turks had claimed. The Swiss engineers noted something else too. The Karakurt's design philosophy was fundamentally different from their own. Swiss Alpine technology was about precision, perfectly manufactured components, tight tolerances, specialized infrastructure. The Karakurt was about robustness, slightly looser tolerances that allowed for thermal expansion, overbuilt frames that could handle abuse, AO systems designed to be maintainable with basic tools in remote workshops. One Swiss engineer wrote in his personal notes, "The Turkish approach accepts imperfection in manufacturing, but compensates through intelligent weight distribution and thermodynamic efficiency. Our method demands perfection in manufacturing to achieve efficiency. Both work, but their method costs less and requires less infrastructure." World War II buried the story. Turkey remained neutral, but its railways focused on domestic needs. The Karakurts kept hauling freight through the Taurus Mountains, unnoticed by a world at war. By the time peace returned, diesel-electric locomotives were emerging as the future. The international railway community moved on. The Swiss continued to export their Alpine technology. The Karakurt remained a Turkish phenomenon, unknown beyond its home rails. The locomotives worked until the late 1960s. Karakurt number 1 was scrapped in 1967. Number 3 lasted until 1971, ending its career hauling coal trains in eastern Anatolia. None were preserved. The technical drawings were lost during a reorganization of the Sivas workshops in 1982. The test reports that documented their performance against Swiss technology remained in archives that few researchers ever accessed. Today, if you search for Turkish steam locomotives, you'll find mentions of imported German and British types. The Karakurt appears in footnotes, if at all. Swiss Alpine railway technology is celebrated in museums and documentaries. But in 1937, for a brief moment, a group of Turkish engineers working in a workshop thousands of kilometers from the Alps proved something important: that innovation doesn't require Swiss precision or German resources. Sometimes it just requires engineers who understand their specific problem deeply enough to solve it in their own way. The paradox persists. Switzerland built an entire railway culture around conquering the Alps. Their technology was exported worldwide, from Argentina to India. But when Turkish engineers faced their own mountains, they developed a solution that matched Swiss performance using different principles entirely. One approach became famous, the other was forgotten. The Karakurt's legacy isn't in preserved examples or museum displays. It's in the principle it demonstrated, that mechanical excellence can emerge from necessity rather than tradition, from solving specific local problems rather than applying universal solutions. The Swiss conquered the Alps with infrastructure and precision. The Turks conquered the Taurus with weight distribution and thermodynamic efficiency. Both worked. History only remembers one.